Okay. Well, we're back in class. Just give me a minute here. So the problem usually is that we have to accommodate people that are online, and at the same time, we have to be here in person as long as possible. So let me see how many people are new for this class. How many people didn't take Physics 111 last semester with me? Oh, quite a few.
It's not as pre-marked, is it?
So you probably took 111 with a different instructor, different year. It will be difficult for you to get back to speed, but we're going to do our best, I guess. So the textbook is Cotnell and Johnson, the 10th edition, exactly the same textbook that we used last semester. But this is the official textbook. You don't need to spend $200 to go and buy this textbook. I sent an email today about WebAssign. I hope that they didn't increase the prices. I tried to figure out how much they are going to charge this semester for WebAssign.
It looked like it was the same.
The same price. Well, it is still expensive, but it is less than the alternatives. Register for WebAssign. Last time I checked, 15 people have already registered. So register for it. The homework assignments are there. The first two homework assignments are posted. The first homework assignment is due on Friday this week. And well, we're going to proceed pretty much the same way like the previous semester. So the syllabus is posted there. The syllabus is pretty much the same like the first semester. Since we have quite a few people that haven't taken the class with me, let me go quickly over the syllabus. And let's see. Ooh, this is kind of. Okay, that's a big surprise. We don't have. We don't seem to have. Maybe it's projecting anymore, huh? Let's see. Okay, so basically, we're starting with chapter 18 from the textbook. And practically most of the semester is going to be on topics related with electricity and magnetism. So in addition to electricity and magnetism, we're going to cover in some detail the chapters on optics and also a little bit of modern physics, a little bit of quantum mechanics. The chapter that we're not going to cover is the chapter on special relativity, because that material is, well, not very well covered in the textbook, and also this is a material that is not relevant for almost any technical applications that you can encounter. So if at the end of the semester, if we have extra time, I'm going to talk shortly about relativity, but I'm not going to assign homework assignments. or assign any test questions. So, unlike the first semester, we have smaller number of chapters to cover. So since we're starting with chapter 18, we have only 15 chapters or so to cover. This means that the pace is going to be somewhat slower, but it is still going to be a substantially faster pace than would be ideal. So keep in mind that especially the first 10 chapters are abstract chapters, meaning that the topics that we're going to discuss are not topics that you can see with your own eyes. So we're going to talk about electric fields, electric potential energy, and you already understand that all those terms pretty much sound the same way, even though they're quite different. You're going to discover that after the first week, if you don't stay on top of the material, you're going to see that it is going to be difficult to figure out what is going on, actually. The only way to avoid that is to read in advance the chapter. So we're going to again cover one chapter per week. The list of topics, I put them in the beginning of the syllabus. So each topic is 1 week, starting this week. We're going to do at least 3 midterm exams. And unlike the first semester, we're going to do a midterm exam every 3 chapters. So the first midterm exam is probably going to be somewhere on circuits, on the chapters on circuits. This is chapter 20. And I'm going to again post the practice test and the similar pattern as the first semester. Okay, so for people that are new to the class, here is what you have to do in order to register for the class. Well, you have to go to webassign.net and follow the links there. I emailed the class key for the class today. So you can register right away without paying anything. And they give you usually a week or 2 of grace period before they cut you off. So in about 2 weeks, those $91 have to be paid. If you encounter difficulties paying, contact me privately, and we're going to see what we can do. One more thing before I forget. If there is anybody that thinks that the first semester got a final semester grade that is lower than it had to be, please come and talk with me this week as soon as possible, and we'll see what actually happens. Okay, questions and remarks. Any questions about anything related to this class? Yes.
Well, from the last semester, do you have our finals if you want to like look at them?
Yes, the final exams from the last semesters are in my office. You're welcome to pick them up whenever you want. I probably will keep them for another, let's say, 2 weeks, and after that, that's what we discarded.
You have proctors for these exams.
Oh, proctors. Okay, so the proctoring story is a difficult one because it is not a decision that I can make myself. I have to check with my bosses. I really don't know. Yeah.
I noticed in the syllabus that you said that we might not do all of the midterms in class. That it said,
This class has an online section, and only one person is only one person is going to attend this online section, a person that is positive for COVID. So again, you wouldn't benefit. So look, this is a required class, and it is very unpleasant people to tell you, somebody else to tell you what to do, what to study, and what not to study. I understand that, and I understand that many of you resent the fact that they have to take physics. I understand that, and I'm trying to do it to make it as easy as possible for you. But if somebody takes a midterm test at home, and other people are going to take the same test here in class, this is going to increase the level of resentment rather than otherwise. So in cases when people test positive and they have to stay at home, we can privately arrange a midterm, a different version, and so on at home, and so on. But otherwise, try to do the midterm when possible. And of course, the most important thing, try to stay healthy. Okay, other questions? Other questions? So again, try to benefit from this class. If you invest the amount of time that is required for this class, you're going to discover that it is actually something that could be quite useful for everyday life, not only for your major, not only for your professional life, but for everyday life. And where the level of science that we're covering here is pretty much maybe a little bit higher than high school, but not much higher. This is material that every college-educated person should have at least some marginal idea how the things in this world work. So again, homework assignments are posted. Again, we're going to solve homework problems that you decide to bring here in class. Starting the week after next week, we're going to try to do out of class sessions to discuss any problems, any physics or math problems that you may encounter, including problems related with standardized tests like MCAT, GRE, and other tests. Attendance is optional, of course. We're going to find the appropriate day and time for this optional problem-solving session. Okay, other questions? I probably should write down the class key number for people to register for WebAssign, and the class key number should be something like this. Here's the class key.
So that's the email you sent to us already.
In the email that I just sent. ISU 02992765. So write it down if you didn't get the email. Yes.
Are you still doing your brownie points thing?
Yes, I'm going to set up brownie points. Again, if you do the homework and if you take the midterm exams, you're not going to fail. Again, of course, you have to accumulate some number of brownie points so that I could have some justification at the end of the semester to make sure that everybody is going to. Yeah.
Is that gonna be the same Excel link, or will we be sent a new one?
I'll send a new one. I probably even removed the old file. So I'll send the new one because it is a different. It is a different class list, right? We have quite a few people that are new for this class. And again, the best way to communicate with me would be by email and in person. I have official office hours. I probably have to check my schedule to post the official office hours, but they are pretty much Monday, Wednesday, Friday at noon, from noon to 1 o'clock. If some changes are needed, we're going to make those changes. But feel free to talk with me anytime outside the official office hours without appointment. Usually, I'm either in the office during the business hours or I am somewhere around this building or on campus somewhere. Just find me and we can try to resolve any issues that are going to show up in the future. Okay, so let's start with chapter 18, the new material. And so we're going to deal with electricity and magnetism. And the experiment shows that under certain conditions, objects acquire some interesting properties that we call electric charge, electric field, and electric potential. And well, the easiest way to demonstrate how it works is maybe by just taking a simple plastic stick and well, we don't have everything that we need here. Okay. So in order to demonstrate the first manifestation of electric forces, let me get something from the storage room here. Okay, so you see this jar, and this jar is very simple detecting device for electric charges and electric fields. This jar contains two leaves of aluminum foil that you see in the middle. And even though it is made by hand and you can make the same device in your kitchen, this is a very sensitive device. It is called electroscope. So if you go and want to purchase the same electroscope from the internet, it is going to be over $100. And with something like 50 cents, you can construct it yourself. And look how the electroscope works. So you create electric charges very often by rubbing, and you see that when this plastic stick approaches the electroscope, the leaves of the electroscope react. They get repelled from each other. And notice that this happens even if I don't touch the plastic stick with, if I don't touch the electroscope with the plastic stick. So how does this work? Well, the rubbing of materials very often create excess electric charges on this plastic stick and also on the fabric that I'm using. Let's say that this rubbing removes some electrons that are originally on the plastic stick and moves those electrons on the fabric. As a result, the plastic stick acquires a positive electric charge. In other words, it has a shortage of negative electric charges. While the fabric, of course, acquires the negative electric charge appropriately. So when this shortage of electrons in the plastic stick is created, the space around the plastic stick acquires new properties that we call electric field. When the plastic stick, together with the electric field, approaches the electroscope feels the electric field and reacts. Of course, if I touch the electroscope, some of the electrons from the aluminum foil are going to move and try to neutralize at least some of the electron shortage on the plastic stick. And as a result, the aluminum foil of the electroscope is going to have a shortage of electrons. And the result is going to be electric forces between the two leaves of the electroscope. So let's summarize actually what is happening. So the experiment shows that materials contain electric charges. And we know that those electric charges are carried by electrons and protons of the material. So we have two types of electric charges, positive and negative electric charge. The electrons carry negative electric charge and protons have positive electric charge. Well, in some textbook, you can see the statement that actually there is only one type of electric charge, and its anti-charge is also present. So this is a different way of looking at the same story. What is interesting, non-trivial, and still not quite well understood by science is the fact that electric charges are quantized. In other words, electric charges appear only in portions. The smallest portion of electric charge is called elementary electric charge. And the electron has one negative elementary electric charge, while the protons have one positive elementary charge. The value of the elementary electric charge, usually denoted with the lowercase letter e, is 1.6 times 10 to the negative 19 coulombs. So we're going to see that coulomb is the unit for electric charge. The coulomb is not one of the 7 basic units in the SI system, but we're going to define it when we start talking about electric currents. So the electric charge of one electron is negative 1.6 times 10 to the negative 19 coulombs, and the electric charge of the protons is positive 1.6 times 10 to the negative 19 coulombs. All electric charges that you can observe in nature are integer number times the elementary electric charge. In other words, the amount of electric charge stored on this plastic stick is equal to some integer number n times the elementary electric charge, where n is, let's say, 0 or plus minus 1 or plus minus 2 and so on. So again, this is a non-trivial fact. We don't know why fractional electric charges do not exist. Well, you can argue that quarks have fractional electric charge, but this is a different story that we're going to discuss at the end of the semester. The experiment shows that ordinary matter, like this remote control, is electrically neutral. In other words, it contains equal number of positive and negative elementary electric charges. When I take this ordinary matter and rub it with appropriate material, some of the electrons from the plastic stick are going to move to the fabric, and the result is going to be shortage of electrons. In other words, net positive electric charge on the plastic stick and net negative electric charge on this piece of fabric. Now, very often, instead of rubbing two materials, we're going to use some low-tech device that contains a plastic, not a plastic, but this is rubber belt that is going to be rubbed against some material here inside this device. And this rubbing is going to be done by electric motor right here. So there is some rubbing of this rubber belt against some other material. As a result, exactly the same static electric charge is generated on the rubber belt, and that electric charge from the rubber belt is moved to the metal sphere on top. The result is electric charge stored on the metal sphere. And you can detect that the presence of electric charge on the metal sphere, like just by moving close to. And of course, if I touch it, you're going to see that the leaves of the electroscope are going to stay separated. Okay, so I need to discharge this, okay, for the moment. And we're going to, again, deal with this as time comes. A fundamental property of electric charges is that same type of electric charges repel, and the different types of electric charges, plus and minus electric charge, attract. The repulsive and attractive forces are going to be given with a simple formula called Coulomb's equation, which I'm going to write in a minute. Now, how the electroscope works. Here is the electroscope with the two aluminum leaves at the end of the electroscope. When I charge the electroscope by touching the electroscope with a charged object, with the charged stick, let's say the stick is positively charged, some of the electrons from the leaves and from the body of the electroscope are going to flow. Here it is, I'm touching it with a positively charged plastic stick. Some of the electrons from this originally neutral metal body of the electroscope are going to start moving. They're going to be attracted from the positive electric charges. And as a result, you're going to have an electroscope with a shortage of electrons. In other words, you're going to have an electroscope with positive electric charges on it, excess positive electric charges. And now look, on the leaves of the electroscope, you have positive electric charges. Therefore, those leaves are going to repel, and you're going to detect the presence of excess positive charge. So, by touching the electroscope with the plastic rod, I'm charging the electroscope by direct contact. But you already saw that the electroscope is reacting even if I don't touch the electroscope with a charged object. How does this work? Well, now consider the following situation. Here is again the same electroscope, originally neutral. And here is the positively charged plastic stick. Not touching the body of the electroscope at all. But look what happens. The body of the electroscope is made of metal. A basic property of metals is that they contain the electrons that they contain. Some of them are almost free to move in the body of the metal. Well, those electrons from the body of the electroscope feel the electric field, and they're attracted to the plastic rod. In other words, some of the electrons want to get as close as possible to the positive charges. They are attracted by the positive charges on the plastic rod. In other words, they are going to accumulate to the part of the electroscope that is closest to the plastic rod. As a result, you're going to have a shortage of electrons on the aluminum leaves, and the result again is going to be a repulsive force, and you're going to see that the leaves of the electroscope are going to separate. Now, look what you can do. In this situation, while you're keeping the plastic rod close to the body of the electroscope, and therefore you have the separation of positive and negative electric charges on the body of the electroscope, what you can do is you can touch the body of the electroscope at this point with some object that is connected electrically to the ground. The only ground connected object right here is this one. So while the electroscope is in vicinity to the charged plastic rod and reacting to the presence of this charged plastic rod, I can touch the body of the electroscope with a grounded object. And look what is going to happen in this case. Some of those excess electrons from this part of the electroscope are going to move and go in the ground. After that, if I remove, after this is done, if I remove the charged plastic rod, the body of the electroscope is going to still have shortage of electrons. They just flew in the ground. And the result is going to be electrically charged electroscope. So this sequence of events results in a charged electroscope, and this type of charging is called charging by induction. So the first way of charging of the electroscope was just by touching it with a charged object. This is direct charging by direct contact. And the second charging, which requires a sequence of steps, is called charging by induction. So please check again this, the topic of charging by induction in the textbook. We're going to talk again about it, and you're going to encounter it in a homework question, in a quiz type of question, and also in the midterm. So it is a little bit, yes.
Why would the electrons flow into the ground if there's still the positively charged stick near it? Wouldn't it want to further go and transfer its electrons to the positively charged stick?
So the question is, if the stick is still here in vicinity and you touch the body of the electroscope at this point with some metal piece that is connected eventually to the ground, why do those electrons flow this way? Well, you're going to see a little bit later on that electrons choose the path of least resistance. And one of the properties of ideal metals is that they're ideal conductors. So the metal gives a path of least resistance to the electrons, and the result is some of those electrons that were in this part of the electroscope choose to move. Of course, not all of them, of course, but some part of those electrons choose to move in the ground, and the result is going to be an electroscope that carries excess positive charge. So you have to go through this mental exercise of charging by induction. It is probably the first non-trivial phenomenon that you encounter in this class, and it is going to be a very good step to get used to electric phenomena that we're going to discuss probably for the next probably 7-8 weeks. Well, all materials around us can be classified in two large classes. Electric conductors, usually metals are very good electric conductors, and electric insulators, like this, or this, plastic, or any other. A basic property of metals, of electric conductors, is that they contain large number of relatively free to move electrons. We're going to consider metals as ideal conductors. We're going to think about metals as if the electrons are free to move in the metal, in the body of the metal, with practically no resistance. While electric insulators like this plastic, you can put an electric charge on the body of the plastic, but that electric charge is going to stay at the place that you put it. So you can put it just by touching the plastic with an electrically charged object, and it is going to stay pretty much there because it is not free to move in insulators. So in most cases, we're going to consider insulators, electric insulators, are as ideal insulators. So you can push the electrons present in this electric insulators with external electric field as much as you want, but those electrons are not going to move. And of course, there is a third type, important type of materials called semiconductors that have properties that are between insulators and electric conductors. And we're going to shortly discuss semiconductors when the time comes, because semiconductors, of course, are the base of the entire electronics industry. Let's see questions and remarks so far. Yes.
So the equation on the board, what is Q and N?
Okay, so E, what is the equation on the board is the question. E is a notation for elementary electric charge. And actually the same notation E is used for the electric charge of the electron, usually with minus sign as a subscript on top of E. Q, lowercase q or uppercase q is the standard notation for total electric charge on some material. And the total electric charge on any object is integer number n times the elementary electric charge. Integer number n times the elementary electric charge. Yes?
How do you know what number to use for that? For N?
The number for capital N can be any number, usually any large number. In the homework assignment, you're going to have one question, which is going to tell you the total charge on some object is, let's say, 5.2 coulombs. What is the number N? How many excess electrons or how many excess protons does this object contain? So N is some integer number appropriately chosen, usually very large number, in order to generate macroscopic visible electric forces. Now we have 3 more minutes. Let's write one formula, the first formula for the semester. It is a formula that gives you the magnitude of the force that appears between 2 point-like charges, electric charges. Let's say that here you have a point-like electric charge Q1 with value Q1, let's say 7.2 coulombs. And let's say that somewhere else you have another electric charge, Q2. Let's say that the distance between those 2 electric charges is R meters. The experiment shows that if those 2 charges are not in motion, they are fixed, their position is fixed, a force, electric force appears between them, and the magnitude of that electric force is proportional to the product of the electric charges, inversely proportional to the square of the distance between them. And of course, there is a constant of proportionality to make this equation work. The experiment shows that the constant of proportionality, K, has value of 8.99 times 10 to the 9th SI units. And the appropriate SI units are Newton times meter squared divided by Coulomb squared. This is the coefficient of proportionality. Now, this force, this equation gives you the magnitude of the force. The direction of the force we're going to describe with words. If the two charges are of the same type, let's say plus plus or minus minus, the force is going to be repulsive, and it is going to be directed away from the other charge. And exactly the same force, of course, is going to act on the charge Q2. The direction of the force is going to be along the line connecting the 2 point-like charges, and it is going to be repulsive, or it is going to be attractive if the two charges have different sign. Coulomb's law is probably one of the basic equations of electrostatics. On Wednesday, we're going to write Coulomb's law in alternative form. And we're going to talk about different ways of expressing all electromagnetic phenomena that appear in nature. Questions and remarks? Okay, so please register to the website as soon as possible, and see you on Monday.